Hi everyone, my name is Michał. I'm a software engineer on WebRTC team in Membrane Framework, and this is measuring beam performance using Beamchmark. The outline of the presentation is as follows. So we are mostly going to talk about two things. The first one is beam itself. We'll dive a little bit into the beam internals. We'll discuss how beam works under the hood. And the second one is Beamchmark, of course, which is a tool that we created in Membrane Framework for comparing performance across two different versions of your Elixir or Erlang application. I'm hoping to have a mixture of some introductory content as well as some slightly more tricky knowledge, so hopefully there is something for everyone. To begin with, let's consider a very simple scenario in which we have Elixir application that generates pretty big load. Therefore, we decided to do some profiling. There are plenty of already existing tools that you can use for profiling, like eProof or AppProof. You can generate some flame graphs. So let's assume that we did some profiling. We also did some optimizations to our code. And the question is, how can we know whether those optimizations introduce significant performance gains? The first thing that might come to your mind is, hey, let's just check CPU load, and we will see whether it is higher or lower after introducing our optimization. And that's a pretty good idea. However, in case of Erlang virtual machine, it might not be a fully reliable metric. And to understand why CPU load might not be a fully reliable metric, we have to dive a little bit into the beam internals. So let's start with the beam architecture. The following figure presents simplified beam architecture. The main entity here is a scheduler. So scheduler is something that is responsible for choosing process for execution and executing it. In fact, this is a little bit more complicated because it's an emulator who executes the process, but for this presentation we can assume that scheduler does both of those things. Using the default beam settings, we will run a separate scheduler per operating system thread. So assuming we have, for example, a CPU with 4 cores, 8 threads, we'll run 8 schedulers. In Erlang, in general, there are no threads, there are only processes, but those processes are much different than operating system processes. So they are very lightweight processes. Creation and deletion are very lightweight. We can create millions of such processes. And the first thing, very important thing here that we can see looking at this diagram is that we have a mapping one-to-many. So one operating system thread can run multiple Erlang processes. This is important because when we are switching between those processes, we don't have to perform context switch, operating system context switch. So we don't have to go into the kernel mode and go back to user mode. There are basically 3 types of schedulers: normal, CPU, and I/O. So maybe let's start with the CPU and I/O schedulers. They are responsible for executing long-running nifs and beefs mainly. We'll go to nifs and beefs later, and normal schedulers are responsible for executing casual Erlang code. The next thing I think that is very important is scheduling. There is a book called the Erlang Runtime System book written by Eric Stenman, and in this book we can read that scheduling in Erlang is can be described as preemptive scheduling on top of cooperative scheduling. So what are those preemptive and cooperative schedulings? Preemptive scheduling is a scheduling where we have a scheduler who is responsible for choosing a process for the execution, executing this process, and deciding when to suspend this process and give control to some other process. So there is no cooperation from the process side in this mechanism. On the other hand, in cooperative scheduling, scheduler is limited to selecting some process for the execution, but it's process responsibility to give control back to the scheduler. So you can imagine that if we had a malicious process who loops forever, it will make our scheduling mechanism misbehaving. Therefore, this technique is called cooperative because processes has to cooperate with each other to make the whole scheduling process work properly. The question here is why we have combination of those two in Erlang. So in Erlang, we still have a scheduler who is responsible for selecting some process for the execution, but the interruption can be made at certain points, for example, when calling a function or when going into the receive block. Therefore, processes have to be written in a certain way that allows for interruptions. The nature of Erlang code is that you can almost not loop forever. If you want to simulate a loop, you have to use recursion, so this is a function call. And if you go to the receive block, which is blocking, you by definition can be suspended. In this way, Erlang scheduling is also cooperative. The question here is when scheduler can interrupt our process, and the answer is that our process can be suspended at 2 points. The first one is when the reduction counter for our process goes to 0, and the second one is when you go to the receive block and there is no matching message in the inbox. So maybe let's talk about reduction counter. What are reductions? Well, I haven't found exact definition what reduction is. However, at least each Erlang function call can be counted as one reduction. So when our scheduler chooses our process for the execution, it sets reductions counter to, I think, 4,000. And when our process uses all of these reductions, it will be suspended and the control will be given to some other process. The problem here is that with beefs and nifs, because beefs and nifs are functions that are, the definition is provided in Erlang, but the implementation is provided in C. So whenever you call such a function, reduction counter will be decreased by 1. However, we are not able to count reductions on the C side. So badly written beefs or nifs can make our scheduling mechanism misbehaving. Also, prior to R16, the beefs, I think very important beefs like binary to term and term to binary were non-yielding, and they counted as one reduction. So binary term and term to binary are beefs used for serializing Erlang terms into the binary format. And when you pass too big structure, too big Erlang map or list prior to R16, it could make our scheduling process misbehaving. The question is, how can we deal with this? There are 3 solutions. The first one is that we can try to chunk our nifs. In general, it's a good practice or in general, there is a general rule that our nif shouldn't take more than 1 millisecond of time. So if this is possible, we can try to split our nifs into smaller chunks that take not more than 1 millisecond. The other solution is to use dirty CPU and I/O schedulers, which I mentioned before. So those schedulers are dedicated for executing long-running nifs. And the third solution is to use yieldable C functions. So what are those yieldable C functions? Maybe let's start with yielding CFun. So yielding CFun is a tool provided by Erlang, which allows for generating yieldable version of your C code. Yieldable version of your C code works in the following way. In general, our function cannot or does not return in the middle of its execution. So when we call some function, it will return after it finishes its work. However, when we have yieldable version of our function, it can return in the middle of its execution and schedule itself for later continuation. And in the Erlang repository, I couldn't find documentation deployed online, but when you go into the source code, you can find a tool called Yielding CFan, and this tool is responsible for converting your vanilla C code into yieldable version. At the moment, at least listed functions are implemented using yieldable C functions. So for example, when you are inserting something to ETS or when you are using some functions on maps, even quicksort is implemented in yieldable version and used in Erlang term to binary. And because this should be pretty simple, we can take a look at how usage of such tool looks like. So when you go to the Erlang repository, there is this tool yielding CFan, and we can go to examples. There is very simple example that implements SAH cryptographic algorithm. So what we have here, this is standalone Erlang project that implements some NIF. So we can go into the CSRC, there are our C code. And what you can see here, we have our NIF code and SAHA2 directory in which we have our vanilla SAH implementation. When we call make here, what we can see is that we are going to call yielding CFan tool, which is used for generating yieldable version of our SAH function. So when we list, once again, files, you can see that we have some generated files. And when we take a look what is in our NIF code. So in our NIF code, there is one main function called SAHA NIF, and it basically calls this generated yieldable version of our cryptographic algorithm. When we are calling this function, here we are passing number of reductions that can be executed during or inside this function. And when this function ends, we are checking whether we should yield. So whether we should give control back to the scheduler. If yes, well, then we are scheduling execution or continuation of ourselves, and we are just giving control back to the scheduler. So that's how it looks like. The other way of interrupting our process is when we go into the receive block. So we can take a look at the process state machine. I think that this is maybe not, maybe this is pretty obvious. However, I think this is also worth mentioning. So whenever our process is running, it's in state running. So our scheduler is executing this process. And when we go into the receive block, we'll transit to waiting state. When you go to receive block and there is no matching message in our inbox. So we'll go to the waiting state. And when there is incoming message, we'll transit to the runnable state and then to running once again. So I'm mentioning about this because gen server call is implemented under the hood, like it is calling a send to some process and then it is going into the receive block. So when we are doing a gen server call, we'll go into the waiting state for a while. Scheduler will stop executing our process, and when there is a response, we'll go back into the runnable queue, and scheduler will pick us later. The very last thing that I want to mention before going into the Beamchmark topic is busy waiting. So what is busy waiting and why is it important? When scheduler runs out of work, it might be better to do some empty work than going to sleep. And this is because it might be better and it might help us to provide better responsiveness. This behavior is, of course, configurable with proper flag in Erlang. We can even delete it or disable it. And there is also something called scheduler utilization. So scheduler utilization is a metric that tells us tells us how much given scheduler was running some processes. Assuming that we are benchmarking our Erlang virtual machine for 10 seconds and scheduler utilization was about 50%, this means that scheduler was executing some process code for 5 seconds. This scheduler utilization doesn't include busy waiting, which means that it can be lower than CPU load. Because CPU load, of course, will include busy waiting, as we are consuming some CPU cycles, but scheduler utilization will not include this. The other interesting thing is that scheduler utilization can be also higher than CPU load. And this is because when scheduler waits or is waiting for some I/O devices or I/O access, it is considered busy because it is not able to perform any further jobs. However, we will not use in such a case CPU cycles, so CPU load can be lower than scheduler utilization. So this was the first part of the presentation, in which I wanted to show you that looking at one metric might not be the best idea in case of Erlang virtual machine. This is because of busy waiting. This is also because of reductions. It's also important in my opinion that to have pretty deep understanding of how Beam works under the hood. For example, because of dirty schedulers or long-running nifs. So finally, we can move to the Beamchmark. And Beamchmark is a very simple tool created in Membrane framework for comparing performance across 2 different versions of your application. And I think that the best way would be to write a very simple example in which we will show the API, in which we will see the API of Beamchmark. First of all, we have to install Beamchmark. If you are writing very simple Elixir script, we can do this with Elixir mix install. So let's write mix install Beamchmark. This should install the latest version of Beamchmark. Next, we can define some very simple module that will generate some load on our machine. So we can benchmark something. And this module is called scenario, and it has to implement behavior called Beamchmark scenario. And we have to implement only one function here, which is called run. And let's do some pretty straightforward operations just to generate some load. So let's generate some enumerable. And let's do some pretty obvious operations. We'll just use integer power function. And that's basically it. So this should generate some load. We just need to run this stream, and we are ready. And now we can call Beamchmark. So we can do Beamchmark run. We have to pass our scenario, some simple scenario, and now we can pass some configuration options. The first one is delay. So what is delay? Delay is used for, or should be used for warm mapping our Erlang virtual machine. This is important because in general, it's not a good idea to benchmark our application just after starting it. We need to allow JIT to do some work. We need to fill some caches. So we'll delay for 5 seconds. And we'll benchmark for, let's say, 15 seconds. And we can also provide some formatters. I think that we'll use HTML formatter. And the only option that we are going to pass here is auto-open, so we'll see the result of running our benchmark automatically when it finishes its job. Okay, so let's try to run this. You can run this with Elixir, Beamchmark API access. And as you can see, we are first running a scenario, then we are waiting for 5 seconds, and then we are benchmarking for 15 seconds. Okay, and here we are. Here is our report. So at the beginning, we have some information, system information, like which Elixir version we are using or how many cores we have. We have also some configuration options, and then we have metrics. In metrics, we have the reductions number, context switches, and average CPU load. We have also some metrics related to or grouped by scheduler type. So we have utilization for CPU, schedulers, normal schedulers, IO schedulers. We have also weighted utilization, which is average scheduler utilization comparing to the CPU available time. And plots. Here are some plots of scheduler utilization and CPU usage. Those plots are, of course, interactive, so you can, for example, display only one usage only for one core. You can also zoom in, zoom out. You can download this as a PNG file. When you run Beamchmark for the second time, it should also compare results with the previous ones. So we'll see this in a while. You can, of course, disable this behavior. In such a case, Beamchmark will not compare results. I have also prepared real use cases of Beamchmark, so we'll discuss them in a while. So as you can see, we have run Beamchmark for the second time. We have also some comparison. We can notice that in this case, the CPU usage was about 8% higher. We have also some comparison on plots. And that's pretty much it. From other options that you can specify when running Beamchmark, you can also specify some name for easier distinction between different scenarios. And you can also disable comparing. As I said, I have prepared some real use cases of Beamchmark, so let's take a look at them. Here is example report from benchmarking our product, which is a video conference system. In this scenario, we had 6 rooms. In each room, we had two active speakers and 15 observers. So we have something around 100 participants. For each participant, we spawned multiple Erlang processes, and we are comparing behavior of this system using 2 different membrane core versions. As you can see, the version of membrane core without optimization was slower for about 30%. And what is interesting, when we take a look at the plots, we can see that all schedulers were running. So I think that we are using something about 51, 52 schedulers using the old version of membrane core, and something about 38 or 39 schedulers using the new membrane core version. And this is pretty interesting because, as I said, we had multiple processes per one peer, and we had over 100 participants. So you could expect that we will use all schedulers. This was running on a machine with 32 cores, 64 threads, as you can see here. And the reason why it is displayed like this, well, to know that we have to go back to the Beam internals, and this is because scheduler load balancing. So let's go back to the presentation. Here are some tips that I was describing during running the Beamchmark and scheduler load balancing. So the idea is that you will get better performance through better memory locality when processes are on the same CPU. And the result of this is that we are trying to compress work on as few schedulers as possible without overloading any CPU. Techniques for achieving this are mostly task stealing and migration. However, we will not discuss them here. You can read more about them in the Erlang runtime system book. And I think that's actually pretty much it. This was the usage of Beamchmark API. The roadmap for Beamchmark is pretty short at the moment. The only thing that we are going to do when it comes to metrics is memory consumption, and probably nothing more at the moment. Going to the summary, some conclusions from this talk. I wanted to show you that measuring Beam performance requires from you deep knowledge about Beam itself. And it might not be a good idea to take a look only at one metric like CPU load. I think that it's also important to put as many metrics in one place as possible because it's easier to see some correlations. Like when you see also that, for example, you are not running all schedulers, you start asking questions, so you go into the Beam itself, you start reading and you start understanding more. So I think that's all from me. At the end are also some resources I was using during this presentation. And thank you for your time. If there are any questions, I will be happy to answer them.